There we go. Okay, we're good.
All right, let's try this again. Good morning, everyone.
Good morning.
I'm Lili Guerrero, and I'm going to be doing an advanced hot water and ventilation case study. I'll be talking about Coliseum Place. And this is an early rendering of it. It's going to be located in Oakland, California. Here's some project info. It's 100% affordable housing located in an area that desperately needs it. It will be 58 family apartments, mostly consisting of very low-income residents. 20% of the units are allocated for formerly homeless folks, and 25% of the units will be fully accessible. It will be all electric, and it's net zero aspiring.
Are there 2 or 3 bedrooms?
There's 1 bedroom, 2 bedrooms, and 3 bedrooms. So this is the project site in red, and as many of you are familiar with this really popular area in Oakland, you can see the Oakland Coliseum. There's the BART station next to it. There's the freeway, and it's very transit-oriented housing as well. So it's great for everyone, and especially affordable housing residents who may not have access to a car. And it's going to be zoned nearby other affordable housing projects. So we took a look at the energy budget pretty early on. This comes from Redwood Energy, who's partnering with us on this project. Shout out. And all the way on the right is our energy budget, which is determined by the PV that is allowed on the roof. And if you want to be net zero, you have to be below that budget, right? And so there's that dotted line. And so the top load there that's in light purple reflects the option of having all of the cars in the parking lot be electric vehicles and have chargers. So quickly, we have to eliminate that option because that's not net zero. And that's one of our primary goals. And so the darker purple below, it represents the potential of having 6 electric vehicles charged at any given point. And while you might imagine affordable housing folks not being able to, or not typically owning electric vehicles at this point in time, we have to plan for the future where the car prices will go down and become a lot more accessible to everybody. So this is kind of infrastructure planning. Below that in red, which is our highest potential for savings, is our domestic hot water system. So going from left to right, the left option is decentralized heat pumps, which is those packaged heat pumps that kind of look very similar to the gas heat pumps that a lot of people have in their homes right now. The 2 right columns represent the centralized systems, which Sean went into and other folks went into. And so the middle one represents the more idealistic performance. The one on the right is kind of represents a more common outcome. And so we really wanted to dive into the potential for saving energy in our domestic hot water system, because as you can see below, the baseline for space heating and plug loads, common lighting, et cetera, is kind of like stagnant. It's pretty much our baseline. We're pretty much at the lowest energy usage as we can get because the envelope is so tight, the windows are really good, the infiltration rate is also really good. So therefore, the HVAC loads are pretty low already. And so we were like, where can we save money or save energy on our domestic hot water system? So I'll read through this. It's a little shifted here, but some hot water considerations include the fact that you can see there's a lot of potential for energy as mentioned. There's always the question of what to do with the hot water recirculation. As mentioned by Sean and by other presenters, the most previous ones, we talked about the energy penalty that occurs when hot water is recirculated back into the heat pump water heaters. And so you either have to store it somewhere or you have to take the penalty. And so if you store it somewhere, there's a lot of footprint of the building. It's already pretty well spoken for, so that we couldn't afford that from the architectural perspective. And on the roof, we couldn't put them on the roof because we wanted all of that area to be allocated for PV. So that was something we wanted to consider. Another dilemma is, of course, the cost. We had a very tight budget. It's affordable housing. You can fill in the blanks here, connect the dots. And also maintainability. As you have been explained to in great detail, how complex the centralized systems can get. You need a very skilled maintenance staff and very well trained. And so we weren't sure if we were going to have access to that, and to hire some expert on staff is something that we really wanted to avoid. And so as you can see here, you can see that we did some predictions, and over the course of the next 10 to 12 years, eliminating a hot water recirculation system would really bring down our energy costs. So we were really trying to figure out, how do we do that? How do we avoid it from an energy standpoint and from an extra equipment standpoint and extra cost and maintainability? This is how you would pipe and diagram a heat pump water heater system with pumps and storage tanks and additional pipe work and expansion tanks. So if we were to eliminate this recirculation system, we would save ourselves a big headache and extra money. And so we were thinking, how do we do that? And so we were working with Redwood Energy, and they were telling us about this small pipe methodology that they've seen elsewhere. And that if we located the hot water heater close enough to the fixtures, we would be able to completely eliminate hot water recirculation, because we do a home run from each fixture. It's 3/8 inch PEX piping back to a manifold that's pretty centrally located. And as you can see here, I don't think I need to explain the area of a circle to folks, but in case you want a refresher, the diameter really is a significant portion. And so just going down from a 1/2 inch to 3/8 inch is a very significant amount of water that you are saving within the pipe that you don't have to flush out in order to get hot water at your fixture. Yes?
Did you ever go with the wind farm on that?
No, we are going through permitting right now, and so I wanted to go through permitting before I got here, but you know, they take their sweet time. But we'll go through some of the code language shortly, don't you worry. Actually, that's one of our next slides. So we eliminated the trunk and branch system, which has been explained, but it's basically, instead of having to flush this very big diameter pipe free of cold water until you get the hot water, we were able to shrink the pipes as skinny as possible. And so there's several sizing methodologies in the plumbing code. This is the California plumbing code. On the left, in tiny, tiny font, you can see that it is a 1/2 inch pipe that is prescriptively allowed for the smallest connection. And so that table hasn't been updated in a very long time. Gary and Emily's presentation yesterday sort of talked about how antiquated these numbers are and how they don't really reflect the updated flow rates of water. And so what I decided to do to make this code compliant and to make sure that it was to use Appendix A methodology, which is shown on the right. And so in using Appendix A, it tells a very thorough story about what's happening and the relationship between velocity, pressure loss, and diameter. And so with that, we were able to do some pressure calcs and really flesh this out and think this through. And so for a lot of the fixtures, lavatories, and kitchen sinks, we were able to go with 3/8 inch piping.
That's fairly conservative. That's mainly on pipes.
So it says fairly smooth if you see on the top left. Yeah. Right. So PEX is the choice that we went with, and PEX is considered fairly smooth as well.
That's really smooth compared to that.
Right. Exactly. So
you've got it's very.
So we're in good shape, is what you're trying to say.
Yeah, that's what I'm saying. Yeah.
Right. Thank you. So these mini plants here is what we decided to go with because the flow rates were so low, and we were able to locate 3 water heaters for the west wing and 3 for the right wing, and then there's a couple for washers and dryers, or washers rather. And you can see that it kind of looks similar to the previous presentation where you have a lot of skinny pipes. It's like spaghetti running through the floor plan. This is a zoomed in version, and as you can see, there's a manifold here per water heater, and about 2 apartments can share 1 water heater. So initially we were looking at what our hot water wait times are going to be, and we saw that it's going to be quite a long wait. It's 60 seconds potentially for a shower, and 23 seconds for a bathtub. That's if they shared the same pipe, because you have to enlarge the pipe if you were doing 1 valve. And so that bathtub filler requires 7 gallons per minute or so. And so that really drove that shower wait time a lot. And as we've heard, it's very significant amount of water there. And so we were thinking about, how do we reduce that wait time? And is that an acceptable wait time? Who's to say? It was, we brought this information to the developer, since they were the biggest decision makers here. And in the midst of designing this and calculating these hot water wait times, it was shared with us some of Gary Klein's work and some of Ecotope's work about the boundary layer, and how actually there is several viscosities happening with cold water and hot water. And as you can see in yellow, that's the hot water that's kind of piercing through, and then on the perimeter is this like more viscous cold water. And so in the center, it just shoots to the end, and in total it takes about 50% longer than expected, than just calculated without the boundary layer. So you have to be very conservative with these and really think about what's the worst case scenario, that the hot water actually ends up at the fixtures. So we were considering all of these things, and so we looked into piping the shower and the tub filler separately. So there's an added cost there, but we think that with these this mitigation of wait times, that it's an acceptable amount of time. And so here are some worst case scenario wait times at the furthest fixture. It's about 60 feet away. We estimated the worst case, again, about 10 feet per elbow. And there's only 2 feet of elbow because it's PEX, and so it's very flexible. And so at worst, it would be about 27 seconds for a lavatory, 15 seconds for the bath, and 36 seconds for the shower. So we brought this to the owners, and we were expecting kind of a lot of hesitancy or pause from them. But they were actually very pleasantly surprised that, you know, this is a bit of a trade-off of waiting longer for hot water and also wasting a bit of water. But they thought that it was well worth their time, or well worth their investment of trying this, because for them, a lot of single family homes don't even have recirculation systems, smaller ones. So they're kind of used to this as their own baseline. So they were very comfortable and gave us the okay to move on forward.
Was the owner paying for the water?
Yes. Because this is affordable housing, we don't have that mandate of individually metering the units. And so one other thing to consider with these package, or in general heat pump water heaters, is the ambient temperature requirements. As the temperature and the ambient temperature goes down, so does the efficiency. And so while Rheem, the manufacturer that we're using, says that you can go between 37 degrees and 145 degrees, we've read several papers that say if it's below 50, it really doesn't perform well. And the sweet spot is around 80 degrees. That's where you can get a COP about 3. And luckily, we have a very temperate climate in Oakland, and you can see the average temperature doesn't go really below 58 degrees. And in the winter, or in the summer, it goes about 74. So it seems like our heat pump water heaters are well suited here. And in order to maintain that ambient temperature from the outside and bringing it in and maintaining it within the closet, we had to vent these guys. And as you can see, it starts to get pretty very hairy inside of these closets. The architects want their floor space, and we want to have enough space to maintain and these water heaters. And so we had to do a lot of research on what the best way to duct these are, because there's really not a lot of information given to us by the manufacturer. So we had to really think about intent here and do some sort of ingenuity based design. So that was the water heating situation, and now we're moving on to some ventilation considerations. So housing and urban development has some acoustic considerations because this is a federally funded project. We have to abide by those. And cost, essentially. So cost is highly influential, of course. As mentioned, this is a very tight budget. And this charrette sort of happened right after the wildfires of California. And so it was very fresh and in our foremind of what the effects of toxic air can be. We were seeing it everywhere, and we were really thinking about how do we address this. We have to reckon with the fact that this is the new normal and that we can expect to see smoke incidences very regularly. And so we wanted to give people the potential of sheltering in place if possible. And so with that, we thought at least a MERV 13 filtration system. So if you need some reminder, this is what the Bay Area looked like during last year's wildfire, and it stayed that way for about a week at least. And so this is really a health issue, and this might be the most important consideration when thinking about ventilation. So our base budget, and what we had our price for, was a ductless mini split system. It's very typical for affordable housing. It has refrigerant coming from heat pumps on the roof or a central location. And there's a wall-mounted ducted or ductless fan coil. We would have done, or the option was to do HRV ventilation, balanced. We could do good filtration. So that was a strong consideration. Another option would have been to use VTAC systems, which is essentially like a PTAC, so in that it's packaged, but it's ducted. But as you can see here, it takes up a lot of floor space, and these apartments are already very petite, so it would have really made an impact. And another option in order to reduce ductwork, since the VTAC was already ducted, was to do an exhaust-only ventilation with the bathrooms. But because this is such a tight envelope, relying on infiltration really was unreliable, and actually we weren't sure where the air was going to be coming from. And so we quickly decided that exhaust-only ventilation was not an option, and it didn't meet our filtration goals, and so we axed this option. A third option was to have a central air supply, and it was going to have a little bit more duct capacity in order to be able to have a duct heater at the end. So this would not have provided air conditioning, and also it was very expensive according to the contractor, and so we did not go this route. Also because of the fact that heat waves are becoming more commonplace, and we really wanted people to have, again, the option to shelter in place. So this was not considered in the end. It's met Title 24 on one of our projects. It's performance based on Energy Pro.
The cost here is
So the option that we selected was a balanced ventilation with MERV 13 filtration. And we had, this is when I made this PowerPoint. We're still in discussion about what the best option is, but as of when I made this PowerPoint, we had decided that having a PTAC of an ANOVA one, which has no penetration to the exterior, -2 small round diameters, instead of, it doesn't go through the entire envelope and compromise the building envelope that way. So it really was the best option in terms of PTAC. And then we had some supplemental electric heat, because we figured if you didn't provide heat to the bedrooms, then people were going to do it anyway with a plug-in version, and therefore throw off our electric calculations. And so this was a great middle ground, and we feel confident about our choice so far. Here are some costs that are associated with the net zero options that we chose. So the rooftop PV is a $355,000 ad with a 50% rebate. The funding is to be determined, but this is what we're estimating. A save that we got from not using a recirculation loop and also sharing heat pump water heaters is $180,000 savings. We have mini splits and HRVs. We don't have mini splits, and instead we have HRVs with PTAX, and so that is a $240,000 savings. And we don't have gas to the building, which is great for many reasons, including indoor air quality, safety, and so it's also a bit of a savings. So in short, it pays to be green. And some final lessons learned. As you saw, there are many, many options that you can choose when it comes to MEP systems. But if you really keep in mind and your goals from the get-go and don't lose sight of them, then you can be very intentional about your decision-making and feel confident that you're on the right track. And it also makes it so that you can really plead your case to owners and really talk about the setbacks and the trade-offs, but also the pros, and really paint an accurate picture to why you should be using these energy efficiency measures. And also another thing that was pretty integral to this process was having a synergistic owner who was completely on board, having the architectural team be flexible with us and our ducting requirements and our floor space requirements for this equipment. Having an energy engineer that was very willing to give us pragmatic and also inspiring solutions or options. Really sharing information between people, like I was saying, Gary's information, Sean's information really helped us paint a great and accurate picture instead of an idealistic picture, and so that everyone's expectations are already pretty clear about where the hot water wait times are, for example. And our willingness to try new things. We had a lot of questions and a lot of time spent in designing something that I've never designed, that my peers had never designed. So we had a lot of extra hours spent in education. And so that's something to consider if you're an owner of an engineering firm, is to account for that and provide an allowance for the unknown. And peer review is definitely key. Me and my coworkers you can tend to sort of start to adopt similar engineering philosophies, and you teach one another. So having an outside perspective and an outside firm look at our drawings really cemented that the science was there to back up our work. And we feel much more confident in our design because of that. And finally, the more net zero affordable housing that we have, the lower or no energy bills that we have. There's more money available to build more net zero affordable housing, and you can see that this is something that is very necessary everywhere, but specifically in the Bay Area. So I feel very happy to be a part of this and to be moving towards a common goal of providing safe housing for everybody. Thank you.